día de hoy es el tercer día de las charlas del Fablabs 2023 y queremos agradecerles por su presencia. Igualmente queremos agradecer a Weston Porter, que nos acompaña desde Estados Unidos, está ubicado en Nueva York y es un compañero de trabajo mío y de la anterior maestría que colaboramos juntos. Weston Porter nos presenta: ¿es esto lo suficientemente orgánico? ¿Is this organic enough? Weston es un diseñador paramétrico, fabricador digital y un posible catalizador para la revolución de robots. Weston ha dedicado más de 15 años utilizando nueva tecnología para automatizar tareas analógicas y procesos digitales, dándole poco crédito a sus colaboradores motorizados y computacionales. Se especializa en crear formas, superficies y estructuras complejas y curvilíneas, tomando inspiración del modernismo orgánico, la biología marina y la ciencia ficción de bajo presupuesto. Su trabajo se ha centrado en el arte público, exposiciones en galerías, exhibiciones en museos y otras experiencias inmersivas, empujando los límites de lo que puede ser generado digitalmente, pero realizado físicamente dentro de un presupuesto razonable. Por favor, recibámosle con un fuerte aplauso.
Hello, everyone. My name is Weston Porter, and first I'd like to thank Fablab UDLA for the invitation to speak. My presentation is a little informal. I figured after a brief introduction and a few pictures, I could just jump directly into the software to give a demonstration of the concepts. I'm here to discuss computational design and digital fabrication from my own personal, practical, professional experience in the fields. My career having originated from fabrication and digital fabrication, not architecture, for better or for worse. In some ways, that's a burden. It took me a while to catch up on math, but it gives me a unique perspective of what can actually be fabricated, which is sometimes hard to perceive if you're only on the digital side. So, computational designer, or parametric or generative designer, digital fabricator, these are cool designations. I'd feel very smart about putting them on a business card if I had one, but they grow less applicable day by day as the gates open and novelty on these technologies wane. It's really becoming just design and just fabrication now. These days, an aptitude for embracing and utilizing new technology is anticipated, if not required. Those who aren't adopting these new technologies are quite disadvantaged in my opinion. After all, the Gutenberg press made scribes superfluous. Computer-aided design supplanted drafters, and the future will increasingly become more robotic and generative. I mean, eventually AI will just take all of our jobs, but that's a separate TED Talk from a smarter person, and I'm hoping we still have a little more time before that happens. For now, it's about optimizing human ability, your ability, and taking advantage of human ingenuity. Tools like CNC routers and laser cutters, software like Rhino and Grasshopper, which I'll be demonstrating for you today. I assume most of you already have an understanding or affinity for these design and fabrication technologies and the opportunities that they create. So I'll stop there. I just wanted to focus on one of those opportunities that is personal to me, which is exploring organic or curvaceous geometries and bringing them to life, which can be tricky sometimes. The title of this talk, "Is This Organic Enough?" is a phrase I borrowed from a Grasshopper tutorial by Gediminas Kardikis, which I've no doubt mispronounced. But I actually printed out, let me share my screen real quick. Here we are. So I actually printed this out and posted it on my dry erase board at work. It's a funny, subtle jab at the pursuit of the organic for the sake of organic. In architecture, the ego of who can make the most globular blob. But it's also a challenge both in design and fabrication. Imagining organic forms is one thing. We see them all the time in nature. So we don't have to think too hard. We can just look up at the sky and see clouds. Visualizing them, be it by sketching or 3D modeling, is another level slightly more challenging. But the physical realization of these intentional, digitally planned organic forms at any scale beyond 3D printing is often an incredible feat. That challenge in design and fabrication has pulled me through the years from an entirely analog existence to my current digital obsession. I began my career as a carpenter in the custom door and cabinetry industry, which is a little boring. And initially, I got by just fine with high school level geometry and doodling on scraps of wood. In traditional fabrication, right angles are typically the right angle and straight lines are great lines. It makes sense that we live in boxes and get buried in boxes because those are efficient forms, potentially boring forms, but efficient. You can make them on any table saw or miter saw, etc. I was comfortable in that line of work, but my career branched down a more organic path, and I had to adapt quickly. I began working in exhibition design and fabrication for natural history museums, which you can imagine are very organic themed, in immersive interactive design, which involves anything but expected forms, and into public art and fine art, creating organic and biomorphic structures, and a bit into architecture, building canopies, domes, and curvaceous pavilions. And some of these projects I'll be going into detail into the guts, the files of these, but I can scroll through a few. The fun domes are at the top, but a lot of scenic things, museum experience, anything and everything that I have been able to create over the years. Let me scroll back up to something relevant. Right. So making unusual shapes like these, surfaces, structures, necessitates continuously innovating with traditional fabrication, exploring uncommon materials, learning new software, programming, and embracing robotics. After a career in fabrication, the yearning for more organic projects led me to college for formal design education and ultimately to the Master of Parametric Design at Barcelona Tech, the MPDA, where I specialized in Grasshopper. Again, the tool I'll be demonstrating for you today. I think I have a slide in here somewhere from some of these projects. A couple of pavilions that we did. Yeah, this program was primarily about learning Grasshopper, but we did it in the very fascinating way of examining domes and pavilions. 1 second, please. One second, technical difficulty. Okay, all right, where was I? Right, so before I get into kind of the technical side of things, let me ask, what is organic anyways? Formally speaking, it's probably in the beholder's interest, but generally I'd argue that it evolves with technology. I have accompanying photos for these. So this is a book from 1941 from the MoMA. It has an interesting description of organic design. And you know, in this time, pretty much any deviation from straight lines and right angles, was considered organic. You know, the double curvature of the Eames chair, which was an innovation in steam bending perpetuated by the wartime industry, blew people's minds. This little bit of double curvature right here. Likewise, new industrial tube bending technology It gave birth to Marcel Breuer and Mies van der Rohe's chairs, precedents in furniture design that's continued today. The point that I'm trying to make is technical capability often drives creativity. It either limits creativity or it enables creativity, which is the crux of design. And today, with digital fabrication, rapid prototyping, batch manufacturing, and incredible new materials, that is a high bar for any creative to well and truly exploit. Computational design is part of that answer. It's the peanut butter to digital fabrication's jelly, the yin to its yang, and through both you can push the limits of what can be digitally conceptualized and then what can actually be physically created. You need a plan for that though, and how to realize that. I'm going to go through a few of mine today. For my personal ideology as to what organic is, I'm there with the mid-century furniture. Working in organic on a large scale, it requires quite the investment. Typically, I'll take whatever double curvature or undulation I can get, and a little bit of undulation, anything in the pursuit of asymmetry. Asymmetry is often an expensive luxury, but I will get into that momentarily. So, talking about these organic shapes, I'm going to focus on domes. Let me begin with a geodesic dome. So geodesic domes, while they are faceted, they are examples of double curvature, of discrete translations of spheres. Let me turn off a few things here. So let me get you a little custom with the interface here. So this is Grasshopper, a plugin for Rhino, Rhino being a 3D modeling software. And for the case of these initial three pavilions, curved domes, as you were, this is what I'll be using. And it's somewhat of a flex because in each one of these three files, there was no base geometry involved. So we're generating the shape and then we're generating the parts and plans off of that shape. So I wanted to talk about symmetry and asymmetry first, and the geodesic dome is a perfect place to begin with that. So here in the beginning, we're focused on the form finding. So that would be, the size of the dome and the frequency being the number of these like triangular panels that break it up. Within this geometry, you have the freedom to change the size of this, increase the size or shrink it, or add more frequency. And the rest of the script adapts to build that and ends up spitting out everything you need to actually physically create it. The interesting thing about the geodesic domes is there is a lot of asymmetry. There's a lot of symmetry here. So you have a lot of repetitive parts. So if I scroll out here, go into overhead mode, you see these are the unique struts. In the case of this geodesic dome, the material, rather than buying a dome kit like a reasonable person would be doing, we built it from scratch. The material on this was very structural. It was this a steel T-bar channel, and these were the unique links. Here labeled different colors as S0, S1, S2, and so on. And then next to it, the dimensions. I'm sorry, everything here is in inches. But we do have some decimal places here. So 63.35 is a difficult thing to give someone with a tape measure. 56.97, you can round down, but with structures like these, any small deviations lack of tolerance can cascade and throw everything all out of whack. And this is a discussion about design for fabrication. So let me start there. These pieces you see, these 2D curves, these are CNC ready files, and these are labels for these files. So in this case, we CNC routed out these long sticks to test the fit on the pieces as they come off of the metal bandsaw. Coming upwards, we also have, let's see how many, 1, 2, 3, 4, 5, 6, 7, 8, 9 different hubs. Each one of these nodes has to be a very specific angle. Luckily, we didn't have to make too many of them, but being able to create these and retain this accuracy is, again, really important for tolerances. In this script, the hubs are being created as 3D models, but then we're breaking apart the pieces, individual pieces, and labeling them for the different fins and flanges for the hubs, as well as these CNC routed jigs, which you can see in this photo right here, have some laser cut inserts to line everything up to be welded at the exact dimensions needed to bolt together with the T-bar. So in this case, the script also includes the CNC routed files for these with pockets and labels and the laser cut pieces. Now, this is a pretty easy system. We don't have that many parts. We could basically just look at the map of these pieces, color coordinate it to the pieces and build this. I mean, honestly, geodesic domes are straightforward enough that you wouldn't necessarily need any of this at all. You could just take the links and do a little math and figure out yourself. But this was the way I built this script is that I built it for asymmetry. So if I were to take this initial dome geometry and skew it, squish it, scale it unproportionally, if I were to take some of these vertexes and push and pull them in different ways, then after my computer thinks for a long time and potentially crashes, it would recompute everything here. So instead of these, 7 or 8 different jigs, this little yellow line would go off into near infinity. And at that point, it's a risk versus reward. This is where asymmetry gets really expensive. You can make things that are less symmetrical, but then you're looking at potentially each and every one of the parts being entirely unique. But that's not necessarily a problem. That's a problem of the organic in general. But as long as you have a system in place for managing this, then it's not an insurmountable task. A part of what this script does is gives you the cut list, which I had a larger photo, but the cut list for linear nesting. So, if you have someone at a station just working a metal bandsaw all day and they're working on these 20-foot long links, then they would have a map of how long to measure each one and cut it. They would have these story sticks, the plywood sticks, to be able to measure that. The hole placement is standardized, and someone could potentially just assemble these jigs all day long, gather up the plasma cut engraved pieces, and in this regard, you could build pretty much any shape you want, within reason. Torsion and twisting are another issue, but I can reference that on another piece. So the next one I'd like to jump into is this circle packing dome, which gets slightly more asymmetrical. So in this dome, to the photos here real quick. I'll walk you through the process a little bit. All right, so here is the geodesic. Everything came together really well, as you expect with the geodesic math. And this thing was ridiculously strong, stronger than it needed to be. This was the initial installation outside, but it'll eventually be enclosed. So the circle dome surface, as I like to call it, was my thesis project, my solo thesis project at MPDA. And I had the luck of being able to build it at the same time, or shortly after I graduated. This is the aforementioned geodesic in the back here. And I was doing that project for a sculpture park in Houston, and I was kind of able to upsell a 2-for-1 dome special. This one being a lot more theoretical and experimental and nerve-wracking to create, but it turned out all right. So before I jump into the script, I'll briefly outline the direction here. So the idea of the dome is circle packing, but circle packing in a structural way. Circle packing is something that you can think of in terms of soap bubbles, on in the sink, kind of like jostling back and forth for the right position. And that's largely how this was generated. I think I'll take a second to load some of these animations. But it was the idea of generating the surface, capturing the surface somewhere between a plane and a dome, generating the circle pattern somewhat randomly onto this dome. I'll have to come back when these are loaded a little bit better. And then optimizing the pattern to be the most structural. The difficulty here was that we're using these steel rings, and the diameters of these steel rings. I've actually got one here, one of the smallest ones, signed by the crew that helped me put it together. But the issue is that each one of these rings couldn't be its own custom size. It needed to be a specific diameter. In this case, I used 3 different diameters. So the computational method had to do with how we're going to fill this space in a structural way to make sure that all of these rings are connecting to their tangential neighbors with enough pieces. Typically, these all have 4 connections each, and considering the outside edge. In this system, I got to explore several different ways of generating these, but the most effective way was through just generating these forms, these patterns randomly, and then coming back and examining what was right about them, what was wrong about them, and then regenerating them. In Grasshopper, the specific tools for this were Kangaroo, which is a physics simulation generator, and Octopus, which is a multi-objective solver. It allows you to create this a circular process of generation, optimization, and regeneration. Some of the example metrics that I use for this are measuring the surface, curvature, visualizing the circles of any given pattern for the planar nature of these rings over curvature. So in areas like this in the turquoise, it's easier to maintain the curvature. In other areas like this in the red, it gets a little bit harder because you're starting to deal with these flat planes. Again, measuring the quantity of these tangential connections, the way that the ring dome was temporarily anchored, but then ultimately welded together. You can see these little butterfly connections here. And lost myself. And trying to predict for aesthetic issues. Unsightly gaps in areas may not be a structural issue, but might be an aesthetic issue along the edge as well. And then the closeness of these rings. which it helps to estimate, how difficult some connections would be. Ideally, everything should maybe almost touch with these rings, but definitely not overlap, because then this ring is jostling another ring out of its place, and very quickly that will cascade around and cause a lot of difficulty. So by optimizing how these were generated, I was able to create a map, essentially, of which rings are being used where and their angles to each other. Initially, I 3D printed these rings and then created a model off of them. The first model I created was very lumpy, as you can see, and I determined that I would need to have an internal substructure, temporary plywood substructure, to make that happen. So walking through that process a little bit, not to speed up a little bit because I'm behind on time, but we created the simple radial waffle structure to support everything, anchored and reinforced that, and then according to the original map, started laying out the different rings, temporarily just zip tying them, connecting them together, and eventually welding each of these together. In some cases, I ran short of rings and we had to factor in some plasma cut pieces, but overall, the map held very true until the very top here. Here's the finished dome and the warehouse, and we left seams in very strategic places so the different panels could be pulled apart, stored, and then ultimately reassembled on site. So again, on the idea of adaptation, here's the model for the ring dome, one of 3 files. This was the process by which the rings were rolled into stacks and then cut, bent back together, and then welded in place. But again, just like the geodesic dome, it's the idea of adaptability and using as many like parts as possible. The radial waffle structure, each one of those pieces were definitely unique. By the way, plywood at this length, it becomes like noodles, essentially. But it was manageable. Each one of these pieces was generated and labeled. Everything slid together appropriately. We had notches generated at the right angles to allow everything to come together. And I chose this shape somewhat cautiously because it was more dome-like, and the more dome-like you are, I guess the more confidence you can have that it won't fall over on you. The egg shapes, hemispheres, domes are just naturally very strong forms. But the repetition of pieces, namely these circles, and the plan for how they are brought together and communicated to those assembling it, was a key feature for capturing this organic double curvature and slight asymmetry, very slight asymmetry in the way that the dome spreads open. So that was kind of a precursor to coming to the third, I wouldn't call this a dome, but perhaps pavilion we have here, which is a prototype I made for a company called Volvax in New York. But this represents pushing the idea of asymmetry a little bit further. This was based on conical research, something that one of my professors at MPDA, Xavier Teller, specialized in, and myself and Danny, another one of my fellow alum, really threw ourselves into, and I essentially had both of their assistants in helping build this, so I don't want to take all the credit. But the key part with this piece right here is really the data management. Once you have something that's organic and potentially asymmetrical, again, every single piece is unique, and it can be difficult to manage all of those. This script here is about maybe 5,000 components. It's hard to show it all. It looks like a mess, just like any script this size could. But there are some unique features in here I just wanted to demonstrate. And again, overall, I'm just discussing these like concepts and how they can make making organic things a little easier. First off, I would say part labeling is the foremost. So I'm going to turn these 3D tags on. So with every single one of the pieces on the structure being entirely unique, it was very important to give each one its own personal label. So this node right here is DR. This vertical strut is V71. This one is H147. And I have the visual map here of how everything comes together. And additionally, I have the flattened out view of what this shape would look like. Again, with all of the horizontals labeled. I have the nodes turned off here as well, but you would see those as well. I did design this in a way to be a little more intuitive for the assembly. That's the second large thing with working with like unique parts like these is how to label them and then how to bring them together. It's the parts and the plans that bring it together. So there is a little bit of a rhyme and reason for this. The nodes start with AA, AB, AC, BA, BB, BC, and then you have horizontal 1, 2, 3, 4, and vertical 0, 1, 2, 3, 4. So if you did start on the corner of this piece, you could work your way all the way around, over this arc and over just following this map. These labels are translated to the parts as they are in 3D space, and then brought down to the 2D plane with the appropriate notches and with all of the labels. So the label of the piece itself in the middle, and then which one of the nodes to the left or right that it connected to. Likewise with the nodes, the name of the node here, and then the name of the connection that it links into nearby. This brings me to the third issue with dealing with this many pieces is it can ultimately become a puzzle. This structure was relatively small, but it was a prototype for what could be a much larger, much longer, much wider piece, or even a smaller piece, but with just smaller quads. So it was heavier and more structural. But if you end up just cutting all these pieces, then you suddenly have a puzzle to deal with. And say you miscut one of these pieces, or you lost one of these pieces, or it's damaged on the CNC router, you would also have a puzzle to be able to go through and refine the exact part you needed. So managing the order in which these are cut, the order in which they're nested on sheets, and the way in which you can find what you specifically need is also an important thing. And that is something I addressed here with a node finder. So the map here, if I wanted to pick an individual piece, I can set it in here, and then it will show me exactly where it is here. Likewise, I could grab a whole section and drop them there. So these, let me clear this off real quick. This helps manage the data, and it's also helpful to use the software to prepare for the actual digital fabrication, which is the one thing I haven't really gotten into as much, focusing on the digital side, but it's through digital fabrication that all these like structures are possible. And it can be tedious, again, with this many pieces if you don't have a plan for that. So if I turn this off and I bake all these pieces, it'll take a moment. If I bake all these pieces, then everything is in its specific layer for how it's going to be cut, and the labels included, likewise for these. There are ways in which CNC CAM software, the software that translates the parts into files for cutting, can be it can be tedious if you don't properly communicate that, and it's even more tedious if you have to go through and click on every single piece within that software. So being able to break things out and recognize them as internal wholes, that don't necessarily need any tabs to hold the piece down, or external pieces that do need little tabs around the edges. When and where the inside of these corners can get the little dog bone. With a rounded bit, you can't always get right into a corner. These are really important things to examine. Likewise, with this particular piece, we explored several different.
Weston, sorry to interrupt you.
Yes.
We have like 3 minutes, maybe
Okay.
maybe 8 if you want, but please.
Okay. Thank you, Danny. I'll wrap up real quick. But just the minor thing, like the last thing I want to mention about, I guess these cones that we made were, again, prototyping a system, perhaps visualizing these as a bent aluminum, but likewise in the file, it is generating all of the different cone shapes, as well as the tool paths by which these are creased along different angles and ultimately cut. So let me wrap up. I could just geek out on the software data structures all day, but let me turn these 3D nodes off. Off. Okay. So again, with these, just to summarize, with these 3 domes, they kind of represent my personal journey into exploring the organic, exploring this double curvature, but pushing the limits of how organic and alien and globular things can be, while still being fabricatable as we go. So I'm hoping as my career progresses, the shapes can get more wild, and there can be more pieces, but I'll always have systems for how these can be managed for fabrication. Let me see if I missed anything here. I think that about covers it. Are there any questions involved?
Tal vez alguien una pregunta. I have a question about
Yes.
your actual job at Anika G Studio. I think it's very interesting the philosophy of your work. What do you think is you can relate digital fabrication and parametric design with the philosophy that is how the dichotomy between nature and robots? How do you see that? What do you think?
Sure, thank you. So let me share real quick. Danny's referring to Aniki Studio, where I've been working for the past, I guess, 4 or 5 months now. Her studio practice is an interesting mixture of new technology. I mean, these paintings here in the back are AI generated CNC carves, and the organic structures here, both organic in their form and topology, are also organic in the materials that are used. In this case, seaweed membranes. This position, it's an exciting one because I get to explore, you know, again, this like dome kind of like a double curvature topography, you know, exploring the organic in form, but also the organic in material, and the alien in many ways, kind of pushing everything to its most bizarre maximal destination, which is, again, asymmetry.
Cool. Thank you very much, Weston.
Mhm.
It's a pleasure for us to have you here. And again, we are here with the Master of Architecture, Advanced Architecture of UDLA. So thank you very much. Please.
Thank you for your time.